Hello and welcome to this new episode of Commodore 64 Games Reverse Engineering. I'm going to be reverse engineering a complete game and providing all of the source code so that you can actually use this source code to then create your other games. I'm going to be looking at the shoot 'em up construction kit. The last video was left with figuring out how the level structure worked within the game and how different parts of the map were assigned to different levels. In this video we're going to look at sprites and animations. This will lead into player and enemy firing and also attack waves with movement. But first we need to understand where the sprites are in the file. We're also going to add a multiplexor or use a multiplexor that I have been working on for quite a while. This multiplexor is quite efficient in how it works. The sort is really quite good and it's able to support quite a large number of sprites with relatively tight packing, so there's no point in reinventing the wheel when you already have a perfectly good set of wheels to actually use. So with the SEUCK editor, this is what the sprites look like that you get in the blank version. We just have a bullet with sprite number 1 and a player ship at sprite 0. All of the rest of the frames are empty. We have sprite 0 to sprite 126. As usual, let's save some base data so that we can do a comparison with it later on, adding some notes to the debug file so we don't forget the range of data that we're looking for later on. There's the default empty blank player sprite. We have these other options in the sprite menu to do with selecting the sprite, editing the colors, and choosing which colors to paint with, for example. Also copying sprites, the kind of standard sprite editor that you would normally expect to see. I'm going to fill in a good portion of sprite 0. Then once that's done, I'm going to fill in a good portion of sprite 126, which is the last sprite. I'm going to use the different color though. I'm going to use general color 3. Now notice here we've got background, 2 general colors, general color 2 and 3, and then changeable color 4. This is aligned with the technical capabilities of the Commodore 64, so background 1 is transparent. It will either show the background color, or if the sprites have higher priority than characters, then it will show the characters behind the sprite. General color 2 and 3. So these are sprite multicolor 1 and 2. These are independent of the multicolors used for characters, and then we have a changeable color which was labeled as color 4, which is basically the color used for each sprite. Whereas the 2 multicolors for the sprite are shared across all of the sprites, we can have a third color which is an independently set color for that sprite in multicolor sprite mode. So that's the data saved out. I also want to find out how to identify these different colors that we're seeing that we can edit here, because general color 2 and 3 are certainly used within the game. So we want to find out where those are set. To be honest, I'm not too interested in background color 1 because that comes from the map and because it's transparent. And I'm not that interested in changeable 4 either because the animation color definitions take precedence over the color of the sprite rather than the sprite in the sprite editor itself. So let's save all of that data and call it colors so that we know that the background, all of the colors have been changed so that we know what we're looking for. And just to really be on the safe side, because I accidentally went to the object menu and I'm thinking that that's going to add some extra complexity to the memory that's been changed. So I'm just saving the colors again, but I've changed the colors that I want to have a look at in the file. So now we're just going to do a comparison between colors and colors 2. Because the editor, when you go into different menus, sometimes it leaves stuff around in the memory. Okay, so because the color data is probably going to be 2 bytes at least, then, or maybe 4 bytes, but probably 2 to 4 bytes because there are 4 values. I want to make sure that it's easy to spot this difference in the files when comparing the files. I don't want to get sidetracked by editor-related data that's floating around in memory. Let's compare these 2 files. First, A number of times I go into the wrong menu instead of the compare tool. It's quite funny. Well, that certainly looks interesting. Some data in the file starts at B71E where the differences are. I have a sneaky feeling that that's going to be the first sprite in the file. This is almost certainly sprite 126 in the file. That certainly looks like the right number of bytes for a multicolored sprite, or a high resolution sprite. Actually, the sprites, if they're high resolution or multicolor, they still take up the same amount of memory. We can see here that there's quite a lot of editor related text, so I don't think that's what we're looking for. The editor related text actually unusually seems to be quite high up in memory. Let's just do a quick memory range calculation with that block of data. 3E, 3F bytes in total then, and yeah, that's basically a sprite data block. Each sprite is 3 bytes horizontally and 21 rows deep, so 3 times 21 is 63, but it's rounded up to be 64 for the VIC addressing mode. I guess internally it was easier than that. And there we go. I think that's the start of memory, so B71C minus 1C plus 900, which is that little calculation we do to convert from the file offset to the memory offset all the time. So we must always remember to do that when converting offsets with this particular file, because we want to document the memory position rather than the offset just within that particular file. In this standard library here, these are the two values really that I want to try and find, the VIC extra sprite multicolor 1 and 2 values. I'm not really interested in the background color or the changeable sprite color, so we'll just look for those in the file. These 4 bytes look quite interesting, don't they? They seem to be the only significant bytes that have changed within or between these two files. We have a few bytes dotted around here and there, but nothing of consequence, and I think that's editor related data again. Those 2 bytes are next to each other, but I don't think it's those 2. It could be. I think we'll need to create some extra test data to really narrow this down. I think provisionally I'm going to document this address offset first, thinking that it's going to be the middle 2 bytes of this 4-byte block that has changed here, applying the file offset to memory address conversion. Provisionally, these 2 multicolor values are going to be that memory address that was just calculated, which was 4081. But I'm not entirely happy that those 2 bytes are accurate, so I think we'll definitely need a little bit of extra test data just to really check this and confirm the hypothesis. So let's go back to the editor again, and this time I'm just going to change general color 2 and 3. So general color 2 and 3 are black and white, so we'll make a note of that first. Black for the VIC is byte value 0 usually, or nibble value 0, because the colors are 0 to 15, and white happens to be 1. So let's change the 2 multicolor values now to be red and, what is this, cyan. Red and cyan happen to be values 2 and 3. So we're looking for 2 bytes of value 0 and 1, changing to 2 and 3. The colors, as they're drawn in the SEUCK editor, are in the same numeric order as they are for the VIC. It kind of like makes sense, right? So here we go. It's that file offset again, but actually the multicolor bytes seem to be separated by 1 byte. So it seems to be that one there. You can see those 2 are changing, but there's a byte in the middle. The 1E byte in the middle has not changed. So okay, here's the color values listed down in labels that you can include in assembly language listings. I have my, as you can see, I had my own standard library which I built up over several years. It's in constant change, but it doesn't introduce breaking changes that often. So anyway, those 2 byte values for the sprite multicolors are in the memory offset at 4081 and 4083. So we have enough information now to be able to load the sprites into the game engine and also set the correct multicolor values. Now the multiplexor that's used for this game, I also include all of the source code for this multiplexor as well. You can see a little demo going here. It shows you exactly how many sprites can be pushed through this multiplexer. The sort time at the bottom is, as you can see, it's relatively quick. So all of this source code is quite extendable. You can choose how to add your own interrupts to the interrupt chain. You can choose how to sort the values, so on and so forth. So adding this multiplexer into different game engines is relatively simple with a bit of programming knowledge. So the sprite data, which if you remember was at C000 in terms of memory address, is being included in the scroller game engine, which in this build is doing the SEUCK engine. So in SEUCK, the sprites start at C000. In my game engine, they start underneath the VIC, in the RAM underneath the VIC registers at D000. That's because usually I want the character set to be at C800 and then the two screens, double buffered screens, at C000. It kind of like frees up the memory underneath the ROM to be used, the kernel ROM that is, to be used by sprites. And I don't change the sprite data. So it makes sense to stuff it underneath the I/O chips, the VIC, for example, the SID, the CIA 1 and 2 registers. It makes sense to stuff the sprites in the RAM underneath those I/O chips because it doesn't get changed that often. Character set data, I want to change it more often, parallax scrolling, for example, and stuff like that. So just adding a little bit of extra documentation here that the size for all of those sprites, 127 sprites at 64 bytes in decimal each, equals 1FC0 in terms of hex bytes. Those sprite fixed colors are being brought in as 2 individual bytes, and then they are set when the game engine starts into the sprite registers. This is because if the title screen, for example, wanted to have its own multicolors, then it can set those into the sprite multicolor registers. And then the game has somewhere where it can actually pull the real game sprite multicolor register values from. So we do it like that. So the multiplexer was included in the engine, and without any animation routines, we can just add some fixed sprites. Now, I need to set the sprite index, so the sprites start at D000. The VIC bank, which is the last VIC bank in memory, starts at C000. There we go. Don't forget that there are 4 16 kilobyte graphics banks that can be visible in the VIC. So we're using the last bank. So we need to subtract the beginning or the start of that bank from where the sprites are loaded, and then divide by 40 in hex, which is 64 in decimal for the size of each sprite. And then we have an index value that we can use to set for the sprite frame. And in this case, it's $40, which is 64 in hex. So we should see the first sprite being displayed against a scrolling background. And lo and behold, we do. And it is that enemy sprite, the circular rotating one. But of course, there's no animation code, there's no animation data because we haven't had a look at that yet. It's not been enabled, that code. So to really test the multiplexer, what we can do is that we can introduce an extra index register here. We can have a little loop. We can store updated values for the sprite positions for the first, say, for example, 15 sprites by storing these values indexed with $x, because animation Y pos, animation X pos, low and high, animation sprite frame, animation sprite color are just arrays, table arrays, if you like, of values that are mapped back into the multiplexer. I'm adding some self-modifying values here so that I can self-modify the, say for example, the Y position, the sprite frame, the color going into the sprite. I really should also have a separate update for the X position, I think. This CLC ADC #8 basically adds on 8 each time it is updating the sprites into the sprite multiplexer, and there we go. We've got 15 sprites, all of different colors, all different sprite frames. So, 16 sprites in total, because it's 0 to 15, of course. So that's 16 sprites. How many sprites have I configured this multiplexer to use for the scroll entry circuits? Multiplex items equals 32. So okay, so let's change that to be multiplex items -1. So we go from 0 to whatever that is, or rather whatever that is, -1 to 0. Let's set up some more sensible positions for the starting sprite position in the Y and the X, so that we get the maximum number of sprites on the screen. So there we go, we'll do that. And we'll also have an independent value for the sprite X position, and it can start at the border left position as well, I think. We'll just leave it like that. So we have 4 self-modifying values now. Let's add on, well, if we take the number of sprite rows, which is 21, and then divide that by 8, which is the maximum number of sprites per line, then we have a minimum packing distance of 2 pixels per sprite if it moves vertically. So I think 4 hopefully should be relatively quite safe. And the X position can be updated 8 pixels horizontally as well for each sprite that's output to the multiplexor. And now we should have a lot more sprites visible on the screen at different positions. And there we go. We have a slight little flickery sprite there in the middle of in the slight latter half of the formation. I have a sneaky feeling that that's probably because the sprites are a little bit too densely packed. Let's change that to add with carry 5 rather than 4, and then that should clear up that last little remaining problem there. It's just that there were too many, on certain occasions, there were too many sprites on a horizontal scan line, so it was skipping it. That's because the screen is scrolling underneath, and the bad lines, which occur every 8 pixels vertically, take up a lot more cycles from the CPU, so it's less able to update the sprites correctly. So this is kind of like the minimal pack, not quite minimal packing, but minimal packing with screen scrolling going on behind it. So we know that the multiplexor works nicely with the rest of the game engine. So that's a good little initial test, if you like, of getting the sprites from the SEUCK editor into the game engine. So that's sprites done. Now let's have a look at reverse engineering the animation data. This is also going to get quite complex, or complicated rather, because I don't know if it's going to be more or less complex than the levels data, but we'll have, it's about the same complexity, I think, to be honest. So let's use the demo game 1 so that we have some interesting graphics to look at. And we've got this edit object menu here. Let's take a screenshot of that so I don't forget what it is. I usually forget these key bindings, you see. So we have select object, test object, setting the animation type, the speed. We can test the object. So if I move the joystick around, you can see the actual object animating as if it's receiving the movement inputs. We can change the color for the animation, which of course changes the sprite color. We can change which sprite frame goes into which particular part of each section of the animation. The player character in this is directional. So say for example, if I put the enemy object into different slots here, then that enemy sprite could go into one of the player animation slots, for example. We have got player animation, player bullet, and player death, and then we've got player 2 animation, bullet and death. We have 8 explosion animations, and then we have a whole bunch, enemy death rather, and then we have, basically usually you draw an explosion, right? But it doesn't have to be an explosion, it could be something else. And then we have the enemy bits, which are for the enemy types. So we have actual enemy type 1, for example, all the way up to 20 or 30 or whatever it was. The enemy types, only the enemy types have these extra bits, which basically say what the collision should do. But we're not going to have a look at too much at the enemy bits, because that is an extra modifier on top of what the visual animation looks like. So we'll tackle that in a later video, because it's related to the attack waves as well. So if we change the animation type, we've got sequence 1, which is 1 frame sequence, then sequence 2, all the way up to sequence, 18. And then we have directional. So we have 8 directions plus the middle one, which is 9 directions, and up to 2 frames for each direction plus the middle one. So that's 2 times 9 frames in total, which is 18 frames, which is the maximum number of frames that we have in the sequential animation. So you can probably guess from how this is looking that the memory representation, the bytes used for the sprite frames are shared between the directional and the sequence animation. And if you change the type, then it doesn't lose the data, it just reformats it to look different in terms of if you're using directional hold or a directional animation, or if you're using a sequence. So the actual object, if you're using directional animation, will revert back to the middle frames, the idle position if you like. If you're using directional hold and then moving the graphic around, then directional hold will stick in that direction. That means it's basically the player will not go back to that central position in the idle frame. It will stick in one of the directions that you've last moved the player. So the demo game 1 doesn't use directional hold, I don't think. I think it uses directional, so that when your player ship is idle, it goes back to looking like a large player ship, and then moving left and right and then releasing it again will show different animation frames. Whereas in the Outlaw and Transputer Man example games, for example, directional hold is used because they tend to be little characters that are running around with arms and legs that like run around and stuff like that. I'm just going to double check that in the documentation. So yes, it says here that directional hold will make your object stay, there we go, in its last position when the joystick is released, whereas direction will go back to the idle frame. So that's useful to know, especially when movement starts being added to the animation engine part of the game engine. If I take the sprite number 0, which is the circular enemy, and then I put it into a particular slot for when you hold, when you are using joystick or movement to input the right hand animation frame, then you can see here that the actual object changes. So when I'm moving the joystick right here, then we can see that the animation is showing an alternation between the circular sprite and the player sprite. Whereas if I change it to directional hold, then the animation frames for that get stuck. If I let go of the joystick, I'm not doing anything with the joystick, it's still showing the circular animation frame for the enemy. So that shows that the directional hold animations don't revert back to their idle frame, which is the middle part. So that needs to be noted down in the little debugging file. So going from directional hold to, say for example, directional doesn't change the animation data. And if I go to sequence 18, you can see there that the circular enemy was present in the sequential data, so that kind of like shows that the sequential data and the animation hold data uses overlapping memory. Okay, so that's going to make it easier, right, to understand how the memory layout works for each animation frame. I'm just noting down here the observations for ship bullet death animation frames ×2 for player 1 and player 2, and then there's enemy bullet 1 to 8, and then there's enemy death 1 to 8, and then actual enemy as well. These are the number of animation frames that we can expect to see. So actual enemy number 1 all the way up to actual enemy number 36, which is object 57, and the player 1 ship is object number 0. So in total that's 58 objects, right? Let's just double check that. 6 for the players plus 8 plus 8 plus 36. Yep, that's right. Equals 58. So yeah, those numbers all kind of like work out. So the thing to work out here also is the animation speed. So we'll tweak the animation speed all the way down to 1, and we'll save that file. So we'll do a comparison for a byte value changing from 6 to 1. Also the color from, say for example, from orange to red. The same thing as before that's been done in the previous videos is you change little things and then you just do a binary compare to see where they live in memory, or the file offset, which is the memory address. So let's change directional to directional hold first of all, and also save that using a useful file name of directional to hold or dir to hold. Then let's change directional hold to sequence 18. All right, I'm just looking at these sprite frames. It would be useful, right, to know which directional and directional hold sprite frames map to which index within this table here. So let's change the minimal amount of data first and just say, for example, save that as sequence 18 because it's coming from directional to sequence 18, right? Let's save that as sequence 1 so that we're just basically incrementally checking these little pieces of information. So now I'm taking sprite 0 and putting it in the first slot, sprite 1 putting it in the second slot, sprite 2 in the third slot, sprite 3 in the fourth slot, 5, fourth slot, sprite 6, fifth slot, because the sprites start counting as 0, so I might as well, and index counting in computer memory terms usually starts at index at 0 as well, because it's 0-based counting. So I'm just putting all of the sprites, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14, 15, 16, and 17. So hopefully, if it's all laid out in memory sequentially, then I should see a block of memory that contains the values 0 to 17, right? In theory. We can see if I change it to sequence 18, you can see and you can see here, oh look, how the directional and probably directional hold animation frames are laid out in terms of their sprite index values now as well. That makes it really very, very obvious, doesn't it? So we've got 0, 1, 2. From the top left, we've got 0, 1, 2, then 3, 4, 5, and then 6, 7, 8. That's the first frame, and then the second frame is 9, 10, 11, 12, 13, 14, 15, 16, and 17. So let's just take a screenshot of that, and we can just put that in the document because that makes it incredibly obvious, rather than trying to write it down as a long verbose description, right? A picture paints 1,000 words, basically. So let's save that ascending sequence data as well as a separate file. Now we do a binary comparison from the base data to the file, which indicates a speed change of 6 to 1. So we look for a byte changing from 6 to 1, and I'm pretty sure that it's going to be obviously in that animation data block. And there it is. There's a single byte changing from 6 to 1. I think we can pretty much safely say what that is going to be. The bytes before it look like animation frames, or sprite frames rather, which is almost certainly the case. These ones don't look interesting. Those don't look interesting. Those definitely don't look interesting. This is all going up into graphics data and editor data. Not interesting to me at all. So let's work that offset back into the memory address 2C92. So we'll note that down in the debugging file, like so. Then we can check between the speed change and the color change from, orange to red, as it says in the file name. Orange is 8 and red is 2 in terms of byte values. And there we have it. Just looks like the lower nibble. Each byte, each half of the byte is a nibble. So 4 bits in total, so values 0 to F in hex. That's going to be 2C93. So I think we can safely say that that's what it is. So let's put that in the debugging file. There we go. The lower nibble, the least significant nibble, the first 4 bits of the byte, basically. Then we do a binary compare between the color change, and then to the directional hold change. So look at that, the color hasn't changed now, but the upper nibble has changed from 1 to 3, and that seems to be directional to directional hold change at the same offset, just the upper nibble. So let's write that down in the debugging file. So we get 1 is directional, and let's indent that properly, and then 3 equals directional hold. Now checking the directional hold to sequential 18 change, and we can see that the upper nibble now has been reset to 0. So that seems to indicate that it's using a sequential animation rather than directional. A directional hold is that if that upper nibble is 0 rather than 1 or 3 rather, sorry. So we'll put that little piece of information in the debugging file as well. So checking the differences between sequence 1 and sequence 18 linear animations here, we can see that the last bit, the most significant bit, gets set if it seems to be the end of the animation sequence. That's certainly one way of doing it. I would have just said how many, well, it uses an extra byte. I suppose putting the high bit there just basically causes you to reset if it encounters that value when it's reading it, which I suppose, because it's negative, because it's the most significant bit, then okay, fine. Then that's a little bit more efficient. But it limits you to 128 sprites, or 128, because the 8th bit is used as an end of animation marker by the looks of this. Just counting backwards from the other animation data that has been found, and this seems to indicate the start of the animation frames, right? So yes, that's the sequential data there, or the directional hold data with those index values that we could see from the screenshot that was grabbed a little while ago. Just to really double check, let's check the differences between the sequential 1 animation and then the ascending sequential animations. And look, it's 0, 8, 1, and then 0, 2, 0, 3, 0, 4, 0, 5, and then 1, 0, and 1, 1. Yeah, that upper bit being set is definitely seems to be the end of the animation sequence. The rest of that data is ascending values, right? Apart from the most significant bit being set. And because the sequential data for the animation frames was using sprite 0 to sprite, what was it, 15 or something like that? Sorry, 17. Then, that pretty much tells us exactly where the animation frame data is in relation to the memory map. So 2C80 equals frames, high bit indicates end of animation sequence plus 1, of course. Now we know where the animation data is, we can pull that data in from the file with a little bit of documentation here to remind us actually in the code what that is, and then we get this animation engine.a file, which basically contains the animation initialization, the animation kill everything except the player's routine, triggering the enemies, which we'll look at in the next video, finding a free animation slot where we can allocate an animation that needs to be spawned, for example, like an enemy or a bullet or a player character or anything else like that. So basically we have a whole bunch of tables in memory for the type, frame count, frame delay, frame initialization value, the sprite color, whether or not the sprite is new, all of that kind of stuff is useful for an animation engine. And then basically every frame you tick your table of animation frames to animate them, and you figure out if they're moving or not, or you wait to be told if they're moving, and then if they're moving you apply the relevant directional animation frames. So let's add back in the animation routines and disable that debug pattern for the sprite multiplexor, because we don't need it anymore, because we're going to be getting animation frames from the animation we're going to be getting sprite positions from the animation routine now. We can also start creating or adding back in the player input routines. So init player 1 basically looks for a free animation slot and then puts the player animation values in there and gets the right color and position and all sorts of stuff like that. So this demo code has the notion of a title screen, but the title screen has been disabled for this purpose, for these examples here. Need to initialize the per frame animation update routine as well, so that sprites will animate correctly. The sprite multiplexor also tells us when sprites are colliding with pixel accuracy using the VIC hardware registers, which was an important part of this sprite multiplexor. But now we can see that the player moves around with the correct directional hold, or directional animation type, not the directional hold, of course. So moving left and right shows the correct frames, which is great. And the player code moves around the player sprite. Let's load that ascending sequence animation data, and let's change because it's sequence 1, right? It's only got 1 frame in it. Let's change that so that it will show the whole sequence, so that we can double check that the sequential animation type is working, and we'll reduce the speed so that it doesn't look completely crazy. Let's save that data as just like test, right? Let's load that test data instead of the demo game data. So we'll just add this little line here. There we go. And then if we run that now, the player should be using a nice sequential animation for all of the sequential sprites. There we go, see? So the player animation data picks out the right data from the right position in the all data file, which is great to see. Looking through the player control code, we can see that the fire routine here, it checks the joystick bits for fire, and then it goes down to here. It's got some little debounce checks, and it's got some fire speed checks and stuff like that. But basically at the end of all of those checks, if they succeed, it goes down and it does JSR to animation find free slot with the animation type of player bullet. And then if that succeeds, then it plays a sound effect. It copies over the player position into the bullet animation positional slot. It uses the two index registers X and Y here. So the source index is Y and then the destination index is X. It then copies across the last direction used by the player and sets that into the bullet. For example, at the top of the animation engine source file .a file there, we've got the numerical types for the different animation types there. So player 1 bullet death, player 2 bullet death, player enemy bullet, enemy death, enemy type. So running that now, if I press fire, you can see that the allocated bullet animation is used whenever the players, and then for player 2 as well, the player 2 ship has a different color and different color for the bullets, of course, and using the second joystick in the emulator, then the second player appears as well. So if we comment out the game 1 data and use game 3, which is the Transputer Man game demo, right, then you can see here that the directional hold animation type is used for the player character here. Moving around and then centering the joystick or leaving the joystick idle will leave the player facing in that direction. And the bullets spawn and then fire off in the direction that the player was last looking at. I think we'll leave this video there. We've covered quite a lot of information. I've shown how the sprites and also the animation data was reverse engineered from the save all data file and effectively the memory. Next video we will look at alien attack waves and movement, which is going to get really quite complicated, especially the movement data. So if you like these kind of deep technical dives into Commodore 64 retro games, then please do consider liking or subscribing to my channel, and I hope to catch you around next time. Have a great day or evening wherever you are. Take care.